All right, hi everyone. So I will continue on the topic of mergers, but in this case, not the ones that collapse into neutron stars, but that remain visible as white dwarfs. And this work is based on a paper that showed up on arXiv this morning. And I wanted to thank my collaborators, including two of them are here, Warren Brown and Sylvia Tunen, and also our referee is also here, Kevin Birch, so thank you all. So when we observe single white dwarfs, we assume that, at least I assume that they must have evolved, by themselves in isolation and think of it that way, but it turns out that that's not necessarily true. And here is why. If we look at the multiplicative fraction of the progenitors of white dwarfs, so here's a figure from De Rosa et al. What we see is that, so the solid lines or the dashed lines, they are simulations for clusters using n-body simulations, and that's the expected fraction. Observationally, the blue dot is for A stars, the green one is for solar mass stars, etc. And what we see is that the progenitors of white dwarfs are, usually in binary systems, the fraction is like 50%. But when we look at the white dwarfs themselves in the local 20 parsec sample, Jay Holberg had a statement saying that, well, when we look at it, it's 26%, so much less than their progenitors. So Holberg said there's a mechanism to lose these companions. But they didn't really say what that mechanism may be. So Tunen et al. In 2017 went further, and what they did is they have looked at binary population synthesis, and the top one is the observed fraction. So in the observed sample, the majority they seem to be single. At the bottom is the fraction that you expect from binary population synthesis. And what we see is that there's a large fraction of mergers, 7 to 23%, that appear to be single white dwarfs today. All right, now in a follow-up paper, Temminck et al. Looked at basically what are those mergers coming from. It is not double white dwarf mergers, right? A lot of these are actually dominated by, as you can see in the top here, they're dominated by red giant plus main sequence star mergers that end up as, more massive stars that become, massive white dwarfs. Now, this changes if you look at the most massive white dwarfs, and the expectation there is, double white dwarfs contribute more. And they also produced this figure at the bottom, which I like quite a bit because it tells us exactly what the merger fractions should be based on these simulations. Now, you can see there are different colors, different lines. That depends on what you assume about common envelope. So if you use this alpha parameter for common envelope, how much of the orbital energy is used to get rid of the envelope. So if it's an inefficient process, you get more mergers. So you get something like the green line on top. And if it's an efficient process, then you get basically lower fractions. And in the end, they said 10 to 30% of all single white dwarfs may form through these mergers. So what we did is we looked at the most massive white dwarfs in the 100 parsec sample from the Montreal database. We found 25 candidates. This was based on, we look at the HR diagram, we plot these cooling models from the Montreal cooling models. And then we looked at the ones that are below or very close to this 1.3 solar mass line. We did our selection based on both Gaia and Pan stars to not to miss any of those. We found 25 targets that seem to be above 1.3 solar masses. Now, you may ask, what are these ones that are at the bottom here? Those are the infrared faint white dwarfs. That's a completely different story, but not for this talk. Okay, so we have done spectroscopy, and this is two of the targets. They are DA white dwarfs. There's nothing special about them except that they are very massive. So the most massive that we found has a mass of about 1.35 solar masses, but it's beyond the model grid, so it's extrapolation. But anyway, given what we have, the most massive ones are about at that mass. The question is, are these merger products or not? How can you tell? So Josiah Schwab did simulations of what happens when you have merger white dwarfs, and he predicted that okay, you could have equation in this collapse a neutron star, but if not, then you end up with a massive white dwarf that should spin fast. So the prediction is that if you're looking at these massive white dwarfs, the rotation period may be down to like minutes, 5 minutes or so. And if you compare this to the pulsating white dwarf sample from JJ's work, those rotation periods are very unusual, right? Normal white dwarfs rotate. So if you see something spinning at 5 minutes, it must be from a merger event. And it turns out that one of our targets was discovered to be a fast spinning object. You see photometric variations at that period. And this is, again, massive. And so this must be one of those mergers. And then Ilaria found another one in ZTF, and she'll show us a lot more of them. And then we're like, okay, well, it looks like, you know, these massive white dwarfs tend to rotate fast. There's another way to identify mergers, and that is if you look at the kinematics of our sample of 25 objects. Here is just based on color versus tangential velocity based on Gaia astrometry. The average is about 20 kilometers per second. We have 4 targets among this sample that appear to be, they have large tangential velocities. Now, why does this mean that they are mergers? Well, you can imagine if you have an old binary system lying around, and if they merge and form a young-looking white dwarf, then they would appear as outliers in our selection. So we think that these 4 also come from merger events. And then there's magnetism. There's discussion in the literature that merger events can create highly magnetic white dwarfs. Here are some simulations from Briggs et al. 2015. What they did is they have looked at the mass distribution that they expect to events, which is shown on top, and then compared that to the mass distribution of magnetic white dwarfs, which is shown at the bottom. And you see that they agree to a large extent. So basically we are saying, okay, merger products may also appear to be highly magnetic. Okay, so what we did is we looked at our 25 ultramassive white dwarfs. We have done spectroscopy and time series photometry. What we found from spectroscopy is 40% of our targets are magnetic, which is crazy, okay? If you look at the local 20 parsec sample, it's about 10% are magnetic. Here, 40%, and this is what they look like. For some of them, the field is so shifted that, you know, you don't even see any lines if you especially look at the ones on top. But these are hot white dwarfs, so there's no other way for them to have these spectra unless they're magnetic. So 40% are magnetic. We found one hot DQ. This is what the spectrum looks like. The model here is half carbon, half oxygen atmosphere. So it's a very unusual object. And we know that hot DQs likely come from mergers as well. And then photometry, we found that 5 of our targets are spinning rapidly. This is the best one. This is J2211, which also has a large tangential velocity. So this is showing data from our first hour of observation. What we did is we tend to observe our targets for 2 hours, but after an hour I was bored, so I looked at the data quickly to see if there's anything significant, and I saw this peak there at 70 seconds, and I'm like, well, this can't be true, because our exposure time was 30 seconds. I'm like, well, okay, we need to stop and expose the shorter exposures, which we did. And as soon as we did, we had an instrument problem, and I'm like, we shouldn't have done that. But luckily, we were able to get back on the sky and get more data, and did 15-second exposures, and now we saw this peak very nicely. And then we looked at it again on another night with 10-second exposures, and there it is again. It's a 70.3 second rotation period. So this star is showing these variations because of probably some kind of spot, something like that. And this happens to be the fastest spinning isolated white dwarf currently known at this period. Okay, so here's the sum of our results. Basically, we found 10 magnetic white dwarfs in the sample. So 40% are magnetic. Now, some of these show more than one symptom of being a merger product. We have 4 of them that are they show fast rotation. We have one of these that shows large velocity as well, and then this guy in the middle, J2211, is the best one because It's massive, it's magnetic, it's spinning fast, it has a large velocity, so it's the ideal target. But besides that, if you include everything, we find that 56 plus minus 10% are merger products. And I want to highlight that, among this, basically, if you randomly pick this, right, 20% of these targets are spinning at rates from 1 minute to about an hour. Okay, so what does this mean? If you compare our data point, I admit it is a large error bar because it's based on 25 stars only, but it's still giving us some hints. So if you compare this to the binary population synthesis predictions, we favor lower common envelope efficiency. You're going to hear, there are going to be 2 talks on this tomorrow, which are going to basically, I think, present something similar. But so we basically favor, as you can see, the light green line. So an inefficient alpha prescription, and an inefficient common envelope where you end up with a lot more mergers than the default. So the default model is at the 2 sigma lower limit of our estimate, so we cannot rule it out. Yes, that's true. But if you look at the efficient alpha model, which is the light blue line, that is ruled out at the 3 sigma level. So our result basically supports these low values of the common envelope efficiency parameter. Now, is this seen elsewhere? So here's a figure from 2010 based on white dwarf plus main sequence systems. And again, as I mentioned, there are 2 talks, I think tomorrow, that will see more updated results. But based on that, what they found is that they can get a simultaneous solution to all of these post-common envelope binaries if alpha is somewhere between 0.2 and 0.3, which is, again, from our work, we are finding that that's kind of like what we are seeing as well. So here are my conclusions. We have identified 25 ultramassive white dwarfs within 100 parsecs. We found that 56% come from mergers, and we favor an alpha that is low. And I have a student right now that is basically trying to extend this work to down to 0.9 solar masses within 100 parsecs so that we can sample this to see how that fraction is changing. And I'll stop there. Thank you.
Suggest for whoever asks questions, please say your name and also your affiliation, then ask the question.
Hi, this is Boris. For the magnetic ones, are the ones where do you always detect some variability rotation and the other ones are rotating slowly, or?
No, so if we, for the magnetic ones, we detected variability in 4 of them out of 10.
Okay, but if those are merger products, they should be also rapidly spinning, more or less.
Yes, but the question is, do they have large enough spots to cause any variability photometrically for us to be able to detect it? So it's possible that they may all be spinning fast, but we just cannot tell. It's definitely possible.
I already have my own mic. Do you see any evolution or correlation with the effective temperature? Like maybe if these things are evolving?
What do you mean by that exactly?
If they are mergers and they start out hot and they're going down the cooling track, maybe you might expect something to evolve with age.
Okay, so okay, here's like, for example, we have the color. Well, I guess we can go back to the HR diagram, really. Yeah, so I mean, we're not seeing anything unusual about these systems, so I don't really understand your question.
No, it's like the B field different for the hottest one versus the coolest one.
Okay, yeah. Okay. No, we don't necessarily see that. No. Yeah, so like this is not based on, like this is not a sequence in temperature, right? It's just based on roughly the field strength. Thanks. Yeah.
No, it's fine. I was just going to complement that and ask if there was any relation to crystallization, but you already answered.
Okay, yeah. And the thing is the crystallization. So if you look at Jordi Isern's paper on crystallization and creating magnetic fields, they predict up to 0.1 megagauss fields. These are not that, right? These are like 5 megagauss up to 100 megagauss, whatever. So these are really strongly magnetic. So there's no way this would be due to crystallization. And also, the fact that it's not just they're magnetic, right? A lot of them are also showing other things as well, right?
So thanks a lot. This is a really cool result, I think.
Thank you.
So I have one question, like, is this inefficient, or this kind of very inefficient common envelope parameter, is this consistent with other observational constraints on the common envelope, like post-common envelope binaries or something like this? Or do you need it to be special for this massive white dwarf systems that you look at here?
So this is consistent with what people have been finding. So in the default model that is shown here, alpha lambda is 2. In the green line, it's alpha lambda is 0.25, which is, and lambda is close to 1. So it would be consistent with the findings from these post-common envelope binaries from Zorotovich 2010. And I think, again, these two talks looking at the abstracts, I think they're getting similar alpha values. So it is all consistent with those other studies, yes. And so if that is the case, then we're looking at the light green line in terms of the fraction of mergers among the single white dwarfs. So next time you observe a single white dwarf, you have to consider that, right? Especially if they're massive, right?
The period, it would be really interesting to try to detect radio emission from isolated white dwarf, because you can fold it. Because there has never been a radio emission from an isolated white dwarf. That would be really cool.
Okay, let's talk about it more.
Okay, one last question.
Yeah, we've been spending a lot of time these last few weeks talking about how well we know the masses of magnetic white dwarfs. And in this case, most of your 56% of mergers are coming from the fact that many of them are strongly magnetic. But if half of those are actually 1.0 or 1.1 solar mass white dwarfs that have been blued by their strong magnetism, that would strongly affect this merger rate. So have you given any thought to, what the systematics are and the uncertainty on this, based on, how well we need to know the temperature, therefore, to get the radius, to get the mass for these strongly magnetic ones?
I mean, the merger rate is the merger rate, right? It's the rate among these 25 stars that we looked at. Even if they are a solar mass, it's still are massive. In terms of how well do we determine their temperatures, I'm going to refer to Simone here because we're discussing this earlier. Why do you, what is causing? Well, okay, the magnetic field is going to change the spectrum. But we are using photometry plus Gaia parallaxes. So I don't know if anybody has looked at, the impact of that on the mass measurements. As far as I know, the mass measurements are okay. But I don't know if Simone, you have any feedback on that?
Well, I don't see what Yeah, so I don't know the discussion you had in the last couple of weeks, so I cannot comment on that. But if I just look at the HR diagram, I mean, they're massive, right? I mean, so you would say that the tracks become completely different if you have a magnetic field. That's the idea? Okay. I don't know. Maybe this is something to discuss.
There is a few examples in the literature where you have a break in the spectrum, so the overall spectral energy distribution is different.
And do we have any evidence of that in white dwarfs? Or?
Yes.
Observational, yeah.
Yes, there's I can show you a paper later.
Interesting.
So the break happens in the UV. So I have looked at Galac's data for magnetic white dwarfs, and within the 100 parsec, I found 2 that seem to be. So if I fit just optical versus optical plus UV data, only 2 of them give me a different temperature and log G, and the rest are okay. So it could be a problem, but I don't think it's a major problem. And I can show you a figure later on that if you like.
All right, we'll carry on the discussion during the
right,
coffee break.
thank you.
Let's thank Mukarrama again.